Rutherford alpha scattering experiment. So Rutherford conducted an experiment by bombarding a thin sheet of gold with alpha particles and then studied the trajectory of these particles after their interaction with the gold coil. That where they are, what is the angle which they are, particular angle which they are making with the, after striking with the gold coil. Alpha particles are there. This is my gold coil is there. So alpha particles, when striking with the gold coil, what trajectory or what angle they are making, whether they are deflecting or going downstep, upwards, or they are making an angle like this. Okay. So Rutherford in his experiment directed high energy streams, okay, of alpha particle from a radioactive source at a thin sheet. Okay. So what was the thickness? 100 nanometer. So 100 into 10 to the power minus 9, or we can say 1 into 10 to the power minus 6, 7. Okay. Meters. Okay. Or we can say 100 nanometers. In order to study the deflection caused by alpha particles, he placed a fluorescent zinc sulfide screen. Okay. So we have to, for the fluorescent material, we have to place the zinc sulfide screen around the thin gold foil. Rutherford made certain observations that contradicted Thomson's atomic theory. So Rutherford made certain observations. First of all, major fraction of alpha particle bombarded towards gold sheet passed through the sheet without any reflection. Okay. This shows that most of the atom is empty. Okay. And then he is showing that some of the alpha particles were deflected by gold sheet. Okay. So like first is that atom is empty because major of the alpha particles went without any deflection. Okay. Some places they were reflected. Okay. With very small angles. Okay. Some places they were reflected with very small angles. And hence the positive charge in an atom is not uniformly distributed. So at some angles, very small angle was there, some totally reflected. The positive charge in an atom is concentrated in a very small volume. So these negatively charged alpha particles were deflected at very small angles. So this positive charge is located in a very small area. Very few of the alpha particles were deflected back. That is, only few alpha particles had nearly 180 angle deflection. So the volume occupied by the positively charged atom is very small as compared to the total volume of atom. So if this is my atom, so the positively charged which were deflecting at very small angles or nearly 180 angle was formed. So due to these alpha particles negative rays, it was getting deflected. So Rutherford atomic model. Based on the above observation and conclusion, Rutherford proposed the atomic structure of elements according to Rutherford atomic model. That positive charge is extremely small volume. He made this at the nucleus. Rutherford proposed that negatively charged electrons surround the nucleus of the atom. Okay. These negatively charged electrons surround the nucleus. He also claimed that electrons surrounding the nucleus revolve around it. Okay. So they revolve around it in a high-speed circular path. And he named these circular paths as orbits. Okay. These are particular orbits. Electrons being negatively charged and nucleus being a dense concentrated mass of positively charged particles are held together by strong electrostatic force of attraction. Electrons and neutrons are like electrons and protons are strongly held together by the electrostatic force of attraction. Now the limitations of Rutherford atomic. So he proposed that the electrons revolve around in a fixed path called orbits, but according to Maxwell, accelerated charged particles emit electromagnetic radiations, and hence an electron revolving around the nucleus should emit electromagnetic radiations. Okay, so any accelerated charged particle emit electromagnetic radiation. So the electron should also emit the electromagnetic radiations. Okay. So this radiations would carry energy from the motion of the electron, which would come at the cost of shrinking of orbitals. Means this shrinking should there, and at last they should be collapsing. Ultimately, the electrons would collapse the nucleus. So calculations have shown that as per Rutherford model, an electron would collapse into its nucleus in less than 10 to the minus 8 seconds. So the Rutherford model was not in accordance with the Maxwell theory and could not explain the stability of atom. Okay. So here it is just collapsing with the nucleus in the 10 power minus 8 seconds. So it is not predicting, the Rutherford model was not predicting the stability of atom. Other drawback that he did not say anything about the arrangement of electron in an atom. How they are arranged in an atom. Like electrons, we know the paramagnetic and diamagnetic characters of electrons. And early atomic models were inaccurate and failed to explain certain experimental results. They form the base for further development of the world of quantum mechanics. So although the early atomic models were inaccurate, but they were the base for the development in the world of quantum mechanics. So now we come to atomic number and mass number. Okay. So are always whole numbers because they are obtained by counting whole objects. Okay. Proton, neutrons, and electrons. The sum of mass number and the atomic number for an atom, we know that mass number and atomic number is what the total number of subatomic particles present in the atom. The mass number represents the mass of the atoms in the nucleus, which is atomic mass unit. So first is atomic number. Atomic number of an element is determined by the number of protons. It is used to differentiate one element from another. The mass number of an element is determined by the number of protons and neutrons combined. Okay. Atomic number is just the number of protons, whereas mass number is the number of protons and neutrons. Neutrons are having no charge. The modern periodic table is arranged in such a way that all the elements have an increasing atomic number and subsequently increasing mass number. But do you know that what mass number or even what atomic number is? Okay. So we know that atomic number is equal to the number of protons and mass number is equal to number of protons plus neutrons. An atom consists of electron, proton, and neutron. We know this thing. The number of electrons in the outermost shell can give us the valency of atom. Like oxygen 6, 2,4. Sorry. So 4 is the valency of carbon. The number of electrons in the outermost shell gives us the valency of atom. Similarly, the number of protons and neutrons are associated with the atomic number and mass number of an atom. Okay. So number of protons and neutrons are associated with the atomic number and mass. So we know that the mass number is the number of protons and neutrons and atomic number is the number of protons. So total number of protons in the nucleus of the atom gives us the atomic number. Atomic number is represented by Z. Here the Z is the atomic number. All the atoms of a particular element have the same number of protons and hence the same number of atomic. Okay. So atoms of different elements have different atomic. For example, carbon has atomic number 6, whereas all atoms of oxygen have 8 protons in their nucleus. Okay. So atoms of different elements have different atomic numbers. So the number of protons and neutrons combined to give the mass number. Okay, and mass number is represented by A. Mass number is represented by A. Okay, so here is the mass. Okay, mass number is represented by A and it is the sum of number of protons and neutrons. And atomic number is represented by Z and it is equal to the sum of only the number of protons. As both protons and neutrons are present in the nucleus of an atom, they are together called as nucleons. Okay, protons and neutrons together are called as nucleons. For example, an atom of carbon has 6 protons and 6 neutrons, thus its mass number is 12. Okay, 6 plus 6 12 neutrons is the total mass number of an atom. While the number of protons remain the same in all the atom of an element, the number of neutrons can vary. Okay, thus atom of the same element can have different mass numbers and these are called as isotopes. Okay, isotopes when they are having different mass numbers. The weight of the electron, like isotopes of hydrogen, are there. Okay. So they are having the same number of protons. Okay, though number of protons will remain same, but the number of neutrons can vary. Okay, and this number of neutrons can differ in the can cause the change in the mass number. So weight of electron is almost negligible. Thus, the atomic mass of an atom is almost the same as that of its atomic mass. Okay, so atomic mass means Z is equals to A because the electron mass is negligible. Okay, we take the existence of atoms for granted, yet for centuries no one believed in them. Around 2,500 years ago, Greek philosopher called as Lycurgus and his pupil Democritus put forward the idea of the universe is made up of tiny individual particles, okay, which they have called atoms. And unfortunately, the great Greek philosopher Aristotle did not agree with them. As Aristotle's views were accepted throughout the Europe for almost 2,000 years, the idea of atoms was shelved for centuries to come. Atoms are the building blocks of matter. We have studied this, and they combine in numerous patterns and form different substances. All atoms except this common form of hydrogen contains protons, neutrons, and electrons. And here the isotopes come. Okay, so it contains proton, neutrons, and electrons. The atomic number of an element is equals to the number of protons. Okay, we have studied that Z is the atomic number, which is equals to number of protons. M is the mass number. Mass number is A. So A is the mass number which is equal to sum of the proton plus neutrons in its nucleus. So in a neutral atom, the number of proton equal to the number of electrons in shells. That is the energy level around the nucleus. Okay. So if there is a neutral atom, so the proton and electron should be equal. Positive and negative charge should be equal in order to balance. Okay. So isotopes are atoms with the same atomic number but distinct neutron numbers. Okay. So isotopes are having same atomic number, means their Z is same. Yeah. Okay, so isotopes are having same atomic number, but their mass number is different. Okay. Okay, so if we take the isotope of oxygen, then oxygen is having the atomic number which is Z will come here. Mass number which is our A will come here. Atomic number of oxygen is 8, mass number is 16. Okay. Here the mass number is in atomic mass unit, which is 15.99, which is nearly around 60. Okay. So isotopes are atoms with the same atomic number. They're having same atomic number, but mass number is different because mass number is equal to the number of neutrons. And if the number of neutrons is different, then the mass number becomes different. Okay, so they are having different mass numbers. The average isotopic mass of an isotope mixture for an element is in a defined environment on Earth determine the element's standard atomic weight. Okay, so average isotope mass. So we take the three isotopes of hydrogen, which are deuterium, tritium. Okay, so these three isotopes will take the average of these isotopic mass of an isotopic mixture from an for any element. We can say for hydrogen, carbon in a defined environment on Earth determines the element's standard atomic weight. Okay, this helps in determining the element's standard atomic weight. Okay, so a little more than 3/4 of naturally occurring elements exist in a mixture of isotopes. Okay, 3/4. You can say 3/4 of the atoms are present as an isotope, and the average atomic mass of an isotopic mixture for an element in a defined environment on Earth determines the element standard atomic. Okay. So this average isotope mass, which is the mass of the all the isotopes which are present in a mixture for any element in Earth, is defined by the elemental standard atomic weight. Determines the standard atomic weight, which is equals to the average isotopic mass. So example of atomic number, which is our Z. If oxygen is there, so atomic number of an atom is equals to the number of protons in the nucleus. 6 protons. 6 protons plus 6 neutrons is the mass number, or the number of electrons in an electrically neutral atom. So if it is equals to the number of proton or number of electrons, atomic number is equals to number of, for example, in sodium atom there are 11 electrons and 11 protons. So the atomic number of sodium atom is equals to number of electrons or number of protons, which is equals to 11. Atomic number orbital energy level. When an electron is at a specific energy level, it is more likely to be found in certain portions of that level than others. Okay. So if my electron is in a specific energy level, it is more likely to be found in certain portions of that level than others. Okay. So like there are 5, like sigma, sigma star, pi star, and then non-bonding. So these are the various energy levels. Okay, non-bond, these are anti-bonding, these are bonding. Okay, so bonding, first of all, bonding orbitals will then anti-bonding, then bonding, and then anti-bonding. Like 1s anti-bonding, 2s anti-bonding. So orbitals are the name for these sections. So these are the ways in which electrons are filled with glucose for. Okay, so orbitals are the name for these sections. Sublevels are made up of orbitals with the same energy. Okay. A maximum of 2 electrons can be found in each orbital. We know that 1s, 2s, 2p. So sp, d, and f, 2s, 2p, 1s, 2s, 2p, 3s, 3p, like this. So 2 electrons can be filled, 6 electrons, 10 electrons, 18 electrons, like so. So maximum of 2 electrons can be filled in each orbital. The most common way of showing the arrangement of electrons Okay, so most common way of showing the arrangement of electron in an atom is to draw diagrams. Okay, like if hydrogen is having three isotopes. Okay, protium, deuterium, and tritium. They are having different atomic number, which is Z, but same mass. Okay, which is equals to number of protons plus neutrons. So here the number of protons are different. Protons are 1, 2, 3 because Z is equals to the number of protons. Okay. To write down the number of electrons in each energy level, the atomic number of the element tells us how many electrons. Okay. For example, the atomic number of carbon is 6, 2, 4. So an atom with an atomic number of 12 has an electronic structure of 2, 8, 2. Because in first shell 2 electrons, then KLMN. So KLMN 2, 8, 8, 18, like this 2, 8, 18, 36, like this, like has to be filled. With 2 electrons in the inner energy level, then 8 in the next energy, and 2 in the outer highest energy level. Okay. The simplest way to understand the arrangement is to look at these. So now we come to the difference between the atomic mass number and atomic. So when we want to find out the valency, we look at the electron only in the outermost shell of the atom. But when we want to know the atomic number or mass number, we look at the total number of protons. So notation of an atom. To write the notation of an atom, we need to know the symbol of an element, the atomic number or the mass number. The mass number of an atom goes above the symbol and the atomic number is written as a subscript. Okay. So always, if X element is there, then the mass number goes above the symbol and the atomic number is written as a subscript. Okay, like this. But here they have written as the atomic number, which is Z upper, and the atomic mass as the subscript. Okay. Then calculating the number of neutrons. If we know the number of protons and mass number of an N, we can also calculate the number of neutrons simply by subtracting. Okay. So if you know, if we know the number of protons and mass number, okay, we can calculate the number of neutrons. Okay. So mass number is equals to proton plus neutron. And if I had to find the number of neutrons, then it will be mass number minus protons. Okay. And my mass number is represented by that mass number is represented by A and number of protons. Number of proton is equals to the atomic number. Okay. So A minus Z, which is the mass number minus atomic number, will give you the number of neutrons. Now isotopes and isobars. Okay, these are the various isotopes of hydrogen. Okay. So isobars are elements that have different chemical properties but have the same physical properties. So we can say that isobars are those elements having different atomic number but same mass. So we first we'll look at the isobars and then isotopes. Isotopes are the elements which are having same atomic number but different mass. Okay, so if I'm taking oxygen, so if I take hydrogen, it is having same atomic number but the mass number is different. Okay. The same atomic number downsides. Okay. So atomic number is same but mass number is 2. So we can say that A to Z. They are having same atomic number but mass number is different. Here the mass can be 1, 2, and 3. But in case of isobars, they are having same mass number and different atomic. Okay. So this is the correct way. Here we have to write this as oxygen 16,8, which is showing 16 is showing the atomic mass, which is the Z, and 8 is showing the mass number, or we can say the atomic number, which is 8. So we can say the mass, atomic mass is in the M, and atomic number is in the Z. Here it is the mass number. Here it is the atomic. Okay. So isotopes are from A to Z. First we will write like hydrogen from A to Z, where Z is its atomic number, A is its mass number. Oxygen, if I will write, the atomic number of oxygen is 8 and mass number is 16. Okay. Carbon, if I will write, then 6 is its atomic number and 12 and 13 are its mass number. Okay. So isotopes are having same atomic number but different mass number. Okay. Isotopes are having same atomic number but different mass number. So carbon is the isotope. Okay. Whereas isobars are having same mass number but different atomic number. Okay. Same mass number means we can say that they are having same A but different Z. Mass number is different, atomic number is Z. Isobars are atoms or nuclei of different chemical elements which differ in the chemical property but has the same physical. Okay, so isobars are having different chemical properties with different chemical properties but similar physical properties. So we can say that isobars are those elements which have a different atomic number but the same mass. Isobars, if I will say, for carbon or for any element X, they are having different atomic number. Okay. Isobars, which is bars are down. We can just remember this by a trick that bars are downward. So bars are downward and different. So downward thing, which is the atomic number, is different in case of isobars. Okay. Their chemical properties is different because there is difference in the number of electrons. Okay. It has the same atomic mass but different atomic number. Same atomic mass, mass is same, but atomic number is different. And this is because an additional number of neutrons compensate for the differences in the number of nucleons. Okay. This total number of nucleons are differing. Okay. So why the atomic number? Because we know that atomic number which is equals to Z is proton plus neutron. And if the number of protons are differing, electrons are differing. Okay, so then the neutrons, because if the additional, this is because an additional number of neutrons compensate for the difference in the number of nucleons. Okay. So additional number of neutrons are coming because the electrons are changing. Electrons are changing. Two examples of isotopes and isobars are iron and nickel, both having the same mass number of 58, whereas the atomic number of iron is 26 and the atomic number of nickel is 28. Okay. So if I will say that iron and nickel. Okay. So iron and nickel both are having this mass. 58, 58, but atomic number is 26 and 20. These are our isobars whose atomic number is different. Okay, because atomic number, we have seen that atomic number is the sum of protons plus neutrons. Okay, here atomic number is equals to the number of protons, and mass number is the sum of protons plus neutrons. Okay, so atomic number here we will take that atomic number as the atomic number is equals to the number of protons. Okay, and if the atomic number is equals to the number of protons, then additional electrons has to be added. Okay, in order to compensate the difference in the number of nucleons. Now let us take the example of two things which have the same color, same physical appearance, such that you cannot distinguish between these two. But when you measure the weight of these two things, then you find the difference. You can relate the concept of isotopes with this example. Okay. Same atomic number, but different. Z is same, mass number, atomic number is different. So as we all know that atoms are made up of electron, proton, and neutron. The nucleus is made up of protons and neutrons, and electrons revolve around the nucleus. Atomic mass is the sum of proton and number of neutrons. Okay. So my atomic mass, which is A, is sum of proton plus neutron, and atomic number, which is Z, is always equals to the number of protons. In an element, the number of proton is always the same as the number of neutrons. Okay. Protons are always same, but the number of neutrons keeps on changing. So isotopes are the atoms in which the number of neutrons differ and number of protons is same.